Okay, so we're back talking about roots of variable expressions, and I've got a few more examples up here for us. The first one, the square root of x to the 20th, and if you watched a video previous, then you probably already have the solution to that. Remember, the index of a square root is 2, even though it's not written. So the super fast way I'm going to deal with this, since this is already an even power, is I'm going to say this must come out to x to the 20 divided by 2 power. I'm taking the power on the inside dividing by the index that is shown on the outside, which gives me x to the 10th power. There it is. How can I check? Well, if I square this, I should get what I started with on the inside since I did a square root to get to here. X to the 10th squared is x to the 20th, so yeah, it checks out. All right. So how about this cube root of x to the 20th? Well, 20 does not divide evenly by 3, so I want to come up with the closest multiple of 3 to 20, and that would be 18, and start there. So I'm going to say, okay, let's expand this out to the cube root of x to the 18th power times x squared. I'm trying to get this to a number such that the one left over, x squared in this case, has a power, that's less than the index out there. And now I'm going to separate it into 2 different roots. And you'll probably, as you get used to this, not even do the separating part. You're just going to start going straight to the solution. So it looks like this. The cube root of x to the 18th times the cube root of x squared. This little part is just going to stay as it is because the power on the inside is lower than the index on the outside. But for this one, 18 divided by 3 is 6, so I end up with x to the 6th times the cube root of x squared. And you're going to have to be careful with your notation since there's so many superscripts, the index here, the other guy there. Just make sure you're really clear in your notation so that everybody knows what you're saying. So this is x to the 6th times the cube root of x squared as our, quote, simplified form of this variable expression. Okay, let me move on to the next one. And really, we're just applying the same principles over and over again. I introduced a couple more variables. That's okay. You can still separate this out as the root of this, the root of this, and the root of that. And what I'm looking for, again, in particular, are numbers that are divisible by 5. This one is lower than 5, so there's not much I'm going to do with that y to the 4th. This one is higher than 5, but not exactly divisible by 5, so I'm going to try to get a number there that is divisible by 5. Of course, that's going to be 20, and that'll get us closest to 21. So let me do all the stuff that I'm saying. I'm going to separate it out and call it the 5th root of x to the 10th times the 5th root of y to the 4th times the 5th root of z to the, I'm going to call it 20 times z to the 1st. That gives me my z to the 21st altogether. And for each of these, I can start evaluating. X to the 10th, 5th root of means I'm going to get x to the 10 divided by 5, which is x squared. I can evaluate that root right away. This guy is not going to change because the power of y is lower than that index. So I'm just going to say, all right, I'm leaving my 5th root of y to the 4th power. The next one, instead of separating it out like I have been, I'm just going to do a little circle. Okay. We can do this one, which is why, of course, I separated it out that way. 20 divided by 5 is 4, so if I take the root of that guy, I get z to the 4th power, but I'm left with the 5th root of z. Now, the things that are in roots, this guy is the 5th root of y to the 4th, this guy is the 5th root of z. I'm going to recombine that under one hat that is in the same root. The guys that are on the outside, I'm just going to multiply them together. These are not the same base, so it doesn't change the powers. And my final result do I have enough room? I don't know. I'm going to try to write small. Is x squared z to the fourth times, make this a different color so it's real clear, the fifth root of y to the fourth z. I'm going to call this my fully simplified result of what we started out with. Now, the more complicated the expression gets, the more little in-between ways you can think of to get to that final representation. But as long as you take it through a reasonable and logical form in the middle part, then you should end up with the correct answer in the end. So let me continue over here with our examples. The square root of 8x to the fourth. We're talking about a square root, so in the number 8, I'm looking for a number that is squared. In fact, I'm going to look for the highest perfect square number. And I'm going to say that that's 4. So this is going to be the square root of, instead of 8, it's going to be 4 times 2. I'm going to leave the x to the fourth alone because it's already an even power and the power is higher than the index. Now keep in mind, 4 is 2 squared. So when I take the square root of 4, I get just 2. The square root of 2 squared is 2. The square root of 4 is 2. And let me separate it out. It's so hard to decide which color to go with. Okay. So we've got the root of 4. Let me do the root of x to the fourth next to that. I could have had these guys together. That would have been reasonable. And I'll put the root of 2 on the outside. Remember, when you're just multiplying things, it's okay to switch the order. And so I can do that with these as well. If you got a plus or a minus there, be very careful. A plus or a minus, be very careful. You can't exactly do the same thing, and I'll be sure to cover an example like that. So this is the square root of 4 becomes 2. The square root of x to the fourth is x squared, and we have a root 2 all by himself there in the end. Trust me, the more you do it, the faster you become. You start doing things you didn't know you could do. Okay, last example for this video. The cube root of 64, a to the fifth, b to the third, c to the seventh power. And we can just take that piece by piece. I don't see any pluses or minuses in there, so I'm not worried about that. The cube root of 64 turns out to be an exact number. So this part, I can do that right away. The cube root of 64 is 16. No, it's not. It's 4, excuse me. Oh, yeah. There we go. Say the wrong thing. There we go. Because 4 times 4 times 4 is 64. I was thinking of 16 times 4. 4 cubed is 64, therefore the cube root of 64 is 4. Now how about this a to the fifth? Well, let's see if we can do this mentally. It becomes a little bit more difficult, right? The closest perfect thing to that would be a cubed. So this a to the fifth I can say is a cubed times a squared. And when I do the cube root of a cubed, I get an a, but I'm left with an a squared in here. Let's keep that in mind. Maybe I'll stick that over here so I don't forget. Okay. How about the b cubed? The cube root of b cubed is b. Okay, that comes out. The closest perfect multiple of 3 to 7 is 6. So that means I can take the cube root of c to the sixth power. 6 divided by 3 is 2, so I get a c squared out here. And I'm left with c to the first power in here. Wow. Okay, so expand that out. Take some time with this last example that I did. I was doing it kind of fast, and I did it mentally, so check for mistakes. Sometimes when you do too much in the mind and you don't write enough down, you tend to make mistakes. But I did that just to show you how you might just start thinking of it as you're going through simplification. But sometimes it's better just to write it all out. So I encourage you to do it on this, write it all out, see if you get the same thing I did.